Chapter 6 is fascinating. It looks at the idea of Gibbs free energy and equilibria, but in solution, and in particular acid-base control of life systems. Now, we're familiar with acids and bases in beakers in a chemistry laboratory, and we will come to an understanding of exactly how those reactions occur and what controls acid-base reactions. But it turns out that acid-base reactions play a central role in sustaining life on the planet. An example of this is the chemistry of carbon dioxide in water, because it turns out that carbon dioxide reacts in water to form carbonic acid. But in the larger scope of things, the chemistry of carbon dioxide in water is very important to both the physical sciences and the life sciences. Indeed, the evolution of life processes on the Earth and sustaining it into the future are closely coupled to the carbon chemistry of the oceans. And we can get a hint of that when we look at this diagram. This is an exquisite skeletal structure of a microorganism in the ocean. And these tiny little structures are calcium carbonate. And we'll see how they are formed from the calcium and the carbonic acid structure in the oceans, but remarkably they're also destroyed by the acid character and the degree of acidity of the ocean systems. So this is a question of balance and a question of what's happening to the carbon chemistry of the oceans as we move into the future. We start, as we have now learned to do in thermodynamics, with the Gibbs free energy surface, because that tells us a great deal about what happens. In particular, we know that when we're burning fossil fuels, we're dumping CO2 into the atmosphere in the gas phase. Well, when that CO2 in the gas phase intersects the ocean, it's converted to CO2 in the aqueous phase. And the question then is, what happens to that CO2 in the aqueous phase? Well, Gibbs free energy tells us exactly what the answer is, because CO2 is a reactant, forms carbonic acid H2CO3, and H2CO3 decomposes to reform CO2 in an equilibrium case. But, as we can see from the Gibbs free energy diagram, delta G for the reaction under standard conditions is plus 8.2 kilojoules per mole. That is the difference in Gibbs free energy between the product, carbonic acid, and the reactants, CO2 and water. That's plus 8.2 kilojoules per mole. Therefore, with a positive delta G for the reaction, the equilibrium lies strongly to the left, and only a small amount of CO2 in the gas phase is converted to carbonic acid in the aqueous phase. And that's what drives the carbon chemistry of the oceans, the fundamental relationship made clear by consideration of Gibbs free energy. When we start to look at the way in which the ocean, the carbon chemistry, and the combustion of fossil fuel interact, we recognize that, first of all, about 50% of all the CO2 released from fossil fuel burning goes into the ocean. So only half of it remains in the atmosphere. This turns out to be profoundly important for our steering the structure of energy and climate into the future. When we look at the inorganic chemistry that emerges out of Chapter 6, it turns out that, as we pointed out before, not only is there a delicate balance between the production of living organisms in the ocean and the destruction of the skeletal structure depending on the acidity, but also the example of coral. Coral is very sensitive to both acidity and temperature. So if we take a natural background and we increase the acidity, we very quickly destroy the coral, because the coral is symbiotic with microbes on its surface, and it's those microbes that are destroyed by higher temperature and higher acidity. So many examples exist globally that couple this carbon chemistry into future climate change and the survival of organisms within the ocean. Now, one of the most remarkable stories in all of scientific history involves Arrhenius. And Arrhenius, as we know, established the foundation for acid-base reactions, the theory of acid-base reactions. But in 1896, he made a statement. He said that humanity stands before a great problem of finding new raw materials and new sources of energy that shall never become exhausted. In the meantime, we must not waste what we have, but must leave as much as possible for coming generations. To realize this in 1896 was prescient in a degree that is remarkable. But even more remarkably, he calculated the increase in the surface temperature of the Earth through the release of carbon dioxide and its infrared trapping. And his forecast for the increase in average surface temperature matches very closely to far more elaborate calculations some 120 years later. This story is going to be written irreversibly into the history of science, and it stands as one of the remarkable connections between acid-base chemistry, climate, and the infrared trapping of radiation.